Okay, so today's lesson is about the concept of work. Up to this point in time, I'm sure you would refer to as work as maybe doing homework, writing something down, or even, I don't know, getting into your car and driving to work. And ending up in some sort of building where you might find yourself sitting at a desk and here you are looking at a monitor, and you would be doing what I guess you would refer to as work. But work is not really any of this in the way we normally think of it, but instead work in terms of physics is it's a product of basically a net force on an object. You do work when you have completed something, but in the physics sense is when you move something. So let's imagine in this sense a better representation of work would be a box, and say that you are someone who wants to move that box over a certain distance. And in order to move that box, you're going to have to exert a force. And you will have completed the work once that box has moved that distance. But until you move that box to a new location, you have done no work. In fact, it is when you have exerted that force over that distance when you have completed the work. So to give you a better sense, or to put this into a definition, I guess you would say, is work is done when force acts on an object and the object moves in the direction of the force. We can describe it as just work is equaling force times distance. That, of course, can be written in a much more concise manner if you just use a couple of symbols like W equaling F times D. Work equaling the force times distance. Now, of course, because force is normally measured in the unit of newtons and distance is normally measured in the unit of meters, our unit of work is actually the Newton meter. But you'll come to find that it's also equal to a new unit which you'll be introduced to today. It's called the joule. And the joule is linked to many things within energy, thermodynamics, and such. But for now, I just want you to think about work, the unit of work as being in the joule, and we'll get into all that later. So how was work done, I guess you would say? Well, let's take the situation of the box again. We have a box, and it is to be moved. And here's our little guy, and he really wants to push this box. And so he's going to exert a force on it. Matter of fact, the force he's going to exert is going to be 40 newtons of force. And he is going to push that box a distance of, let's say, 3 meters. Now, he hasn't done any work yet, but as soon as he does move that box to that new location, and it now is here, he has finally done his work. And if you wanted to find out how much work he did, you'd have to use the amount of force he used over, along with the distance that he pushed it over, I guess you'd say. So in this case, the work that he has performed is equal to, of course, our force times distance, which is 40 newtons times the 3 meters. And so the work he has done would be 120 Newton meters, or using our new unit, the joule, be 120 joules of work. Now, this isn't the only way that it can be done. In fact, in this sense here, the box is not told to have a mass, and that could become an important factor. So we're going to try one where we do give the box a mass. And I'm going to flip this paper over here. And instead, we're going to deal with perhaps somebody who wants to lift a box upward. So here's our box. and it's attached to actually a pulley, let's say. And over here are some guys, and they want to lift that box up. They're pulling really hard down. Another guy right here, I guess you'd say. My people are not very good looking, but let's say this box has a mass of 100 kilograms. And we want to raise that box up into, I guess, the back of or on top of this shelf here, I guess you'd say. And there's some people up here waiting to receive it. And the distance from here to here, let's consider that being, let's say 3 meters. I don't know if you can see that correctly. Let me write that a little more clear. D equals 3 meters. And let's go ahead and scratch this out here. So now we have to figure out, well, how much force is actually being exerted here over this distance. Now, we do know that we do have a mass, and we do know that the acceleration due to gravity is 9.8 meters per second squared. Therefore, using Newton's second law, force equals mass times acceleration, we can actually figure out the force needed to at least lift that box up at a constant velocity. So let's do that. And we know that this box, the mass of it is 100 kilograms. And due to gravity, the acceleration of that box is going to be 9.8 meters per second squared going downward. And we need to counteract that with these guys here. So that their force needs to be at least the amount of force that's being pulled down here. And so we find out the force needed to pull this thing up is going to be 980 newtons. Okay, so now we have our force. But we need to multiply that times the distance that these guys are lifting it up. So we're going to take our 980 newtons and we're going to multiply it by our 3 meters of distance so that we can figure out work. Now remember, work is equal to force times distance. So if I take the product of these two things here, I'm going to come up with a new answer, which is going to be 2,940 Newton meters of work done once they lift that box up there. Otherwise, you could consider it being 2,940 joules of work done. And that is how much work is done when these two gentlemen lift that box up. That is the concept of work.